Okay, and then we'll go there. Okay, so we talked about the capacitance, and we said that there are two types of a circuit, either leading or lagging circuit. And the most important thing is we need to always be, almost always in the lagging side, between 90% to 96 lagging. Lagging means you have more inductive reactance versus capacitive reactance. We talked about the capacitive reactance, how to calculate it. Now we're going to talk a little bit, guys, about the inductive reactance. And this is not new information to you. So what happened, guys, inductive reactance is one of the single most important phenomena. Inductive, I said self-induction or mutual induction or self-induction. Because of induction, we have motors. Because of induction, we have transformers. Because of induction, we have generators. So every time, the smarter than Chad Carey, they discovered, guys, every time you make a coil out of a wire, a piece of wire. Every time you make a coil out of it, it creates an electrical resistance, not a material resistance, electrical resistance to the flow of current. This a magnetic field created in the coil that create an electrical resistance, XL, created from this coil. Okay, you want to stay here? Does it want to stay here? So if you have an XL for this coil, so if the current goes right through the coil, it will create a resistance to the flow of current. If there's no current, then there's no resistance in that coil. Unlike the resistance, guys, the resistance stays in the wire regardless of the current goes in or out of it. The inductive reactance, it's a function of current. So if the current is not there, you wouldn't find an inductive reactance. You would not find an inductive reactance. So inductive reactance, we have your inductive reactance in the coil, a mutual reactance between two coils that you can create. Transformer. We can use them also in generators. So inductive reactance is a big deal. Because of that one, you have generators, transformers, and motors. Unreal. The idea is if you have a coil and you put an alternating current in it, the alternating current will basically vibrate and create induced voltage. That's where the induction comes from. Induced voltage in the surrounding, whatever is surrounding. If the surrounding is another coil like this, it will induce the voltage in the second coil. That voltage here will be proportional to how many windings in this coil, and so that voltage. And by doing that, by inducing voltage here, you will reduce the amount of you will transfer the power from one level of current voltage into another level of current voltage through the induction. So that's basically the most important thing about the induction phenomena. Self-induction and mutual induction here. And you guys who talked about that one, voltage induced and current, EMF and counter EMF and so forth. The key point is that I would take from all of this, the key applied voltage and counter EMF and so forth. Every time you have an applied voltage, it will create a counter EMF, a counter voltage opposite to it, and induced voltage, opposite current, and the same thing, you induce current. The whole idea, very simple. Very simple. You have a current going through a coil this way. The magnetic field will induce a voltage in the second coil, voltage. So now we have a voltage in and a voltage out. The induced voltage, different in phase than the applied voltage, 180 degrees or different in phase. And then when you put voltage in this coil, put it next to another coil, you create an induced voltage in the second coil. That voltage is different in magnitude, different in phase. That's we see the signal start at different location. And then if you tie the second coil, guys, to a resistor, what happens if you have a voltage and you bring wires and you tie them across a resistor? What do you have? Current, induced current. And that's the concept of transformer. That's basically the concept of a transformer. Induced voltage create an induced current at different stages. And I'm not going to go through the science behind it, but that's the thing that I want to emphasize. Induced voltage create induced current for us. Okay. All right, let's go back here. Okay, a couple of things that you guys have to take into consideration. Now that's just the inductance, and if you put also a current in a conductor, there's resistance for the conductor, and there's also an inductance through the. There's two types of resistance in the conductor. One coming from the material itself, the resistance. The other one is coming from the flow of current. And every conductor, later on when we start doing voltage drop, guys, it's going to be every conductor in chapter 9, you're going to have an impedance for it. And we're going to be using this impedance to calculate the voltage drop and so forth. So, but for the time being, remember, it's not just the coil that has an inductive reactance. Coil can have an inductive reactance, and conductors, when you have a long run of them, can have an inductive reactance that that will affect the flow of current in it. Eddy current and so forth, the resistance. Okay. The skin effect and so forth. And I don't want to get into, you guys have heard about the eddy current. I'm not going to go to the scientific part of it. I just want you to understand that these are impedances that will be affecting the current as it goes through the conductor, So, for example, the skin effect, the stranded wires, look at that one. The current tends to flow at the surface of a conductor instead of the core of a conductor. This phenomena, guys, believe it or not, the power companies, you know what they do with these power lines? The core of the power line is a steel wire, and the surrounding power lines, the surrounding is an aluminum wire. Anybody can tell me why the core is steel? When they have a run of, say, 1,000 feet run, the steel will hold the wires together in the air, physical weight. So that's where the steel core inside will for carrying the weight, and the surrounding wire, the shell, that will be carrying the current. That's I think it's a great example of skin effect, because your current is going to the surrounding, even though it's surrounding of the wire, but that's so the core, you really don't care if the steel is carrying current or not. You don't care that much. You care about the aluminum around it that's carrying current. The steel is there to carry the weight of the conductor. So that's
So if you have a stranded conductor, it will still propagate to the outer edges.
if you have a stranded conductor, no, it goes by the strand of a wire. By the strand of the wire. So not the core of it, it will go to the strand of the wire. But if you have a stranded conductor, though, that's why the stranded conductor is good, because now you have more surfaces exposed to carry more current.
Why would it transfer from the steel to the aluminum if it stays within the steel strand?
Well, it's still there. It's really the main reason for the steel. It would not transfer. The main reason for the steel is we care less how much the steel is going to carry. It's there to carry the weight of the conductor.
I'm just talking about the properties of it.
Yeah, it's not. And in the steel, it will also, because of a skin effect, it will be carried by the shield of the surface of the steel, not the core of the steel. But your question is, why would it jump from the steel wire into the aluminum wire? It wouldn't. It wouldn't. Yeah, it wouldn't. Effect of shape, conductors. I'm going to go just to the self current counter EMF. Okay, winding a few of these. My intention of this one, guys, is just to get you into the impedance. This is really my intention. Frequency, core material. Between the phases. Yeah. This is a good example, guys, how you can make a better transformer. Hopefully I still have mine. No. It's dancing today. This is a good example why you can have a good transformer or a bad transformer. So as you have done that before, to increase the inductance of this self-inductance of this coil, you can add more coils, or you can make the material different material, or you can or you can increase the current, the amount of current that goes through it, the amount of current that goes through it. And the whole idea, these are all phenomena that you can use instead of, like, for example, instead of putting in air, if you have conductive material right inside the coil, that will strengthen your coil. Who cares? If I need coils, and I'm not gonna, this is supposed to be guys calculation, so I don't want to get into the science of it because we do this one in the basics. But the idea is if you have a coil, a strong coil, who cares if the coil has a strong magnetic field or not? If you need a strong coil, you can push together, open and close a 2000 amp contacts or a 1000 amp contact. So the strength of the coil becomes a big deal. If you have a coil that you're using for a magnetic contactor, so you're energizing the coil, and when you energize the coil, it pushes two contacts to close. So the strength of the coil is a big deal if you're using it as a magnetic contactors. The strength of the coil is a big deal if you're using it for motors or transformers. So at certain time, you need a strength, the coil to be strong. And these are a couple of phenomena where you can increase the coils or increase the, add the conductive material inside the coil. Magnetic core. And all this stuff, I wanna move on to increase the area and so forth. My intention is really get the impedance from there. P counter EMF 180 degrees, inductive reactance. That's what I want from that. Okay, this is really my whole intention, guys, is to get you into the inductive reactance, XL, that we said XL equal pi times 2 pi times F times L. Inductive reactance is an impedance. So the more inductive reactance you have in your system, the more voltage drop you will have in your system. So 2 pi is 3.14 times F, the frequency, time L is the Henry, the inductance of the coil, That's my intention of this. Later on, guys, the reason why I do that, come on, buddy. There you go. The reason why I do that one, because later on when we do voltage drop calculation and capacitor calculation, I talk about the inductive reactance and the effect of inductive reactance in power correction. Hopefully you understand what the inductive reactance is. Every time you have a coil, you have just created an impedance that will prevent the current from going through because of the alternating current, because of alternating current effect. Use of induction, you guys, we just mentioned a couple of things about using induction. Because of induction, you have we're enjoying what we call them when I was in college, we call them electrical machines. Electrical machines are three types. Generators are one electrical machines, motors another electrical machines, and transformers and a third electrical machines. All of them are working on the concept of induction. You bring a current to the transformer right in here and a voltage. This voltage will create, by moving through this coil, will create a magnetic field. This magnetic field induce a voltage into the second magnetic field. This is where the mutual induction happened. And I got myself a voltage on the secondary that's completely different than the voltage in the primary. Here's your transformer. The same thing for motors, guys. You wire all these windings. By wiring the windings, you introduce a magnetic field. The magnetic field will create a magnetic field in the core of a motor. And everybody knows how the motors work. You put wires, you wire the windings over here. By wiring these coils, you introduce induction. You create a magnetic field. The magnetic field will induce a voltage in the rotor right here. The voltage in the rotor, my friends, will create basically magnets, north and south. And then when you have two magnets, one in the rotor and one in the stator, right next to each other, these magnetic fields will interact with each other to get you the spinning mechanism of a motor. Because all this happened because of the induction concept, the concept of induction, mutual induction or self-induction. Power factor, that's what I'm going to do. I'm going to just let you And again, I went fast through this one because not really my intention is not to teach the basics here. I want you to understand that, guys, for engineers, if you're to do engineer at the U of M, induction, electromagnetism, we call it electromagnetism. You spend three courses studying electromagnetism, the flux, the variation of the current, the variation of the voltage, and the inductive reactance, self-induction, mutual induction, all these calculations. So this is a big science. This is a huge science. All what you need to understand is, for you, is because of the induction phenomena, every time a current goes through a coil, it creates a magnetic field that will induce a voltage into the surrounding. Done. That's the whole concept of it. And every time a current goes through the coil, because of the induction, it creates a resistance to the current. The coil will create a resistance. That's as far as we can go in a technical field. Power factor. The whole idea, guys, is the power factor. In the power factor correction later on, we're going to have two phenomena. You're going to have the XL and the XC. XL and XC, capacitive reactance and inductive reactance. Any question, guys, about the capacitive reactance? Every time here at Dunwoody, right now, as we talk, all the air handling units, the chillers, the rooftop units, all these are creating for us, anything that has a coil in it is creating an inductive reactance. Anything that has a capacitor on it is creating a capacitive reactance. Who cares? Inductive reactance and capacitive reactance, they go against each other. They're both great because of inductive reactance. We have generators, motors, and transformers. But the problem with the inductive reactance, it create a phase shift between the current and the voltage, between my current and voltage. Still, who cares, Chad? Who cares if I have a phase shift between my current and voltage, right? Who cares? A phase shift between your current and voltage, guys, create a lower power factor. Again, still, who cares if I have a lower power factor? A lower power factor, meaning if you take 100 amp from Excel energy, take this, you have 100 amp from Excel energy. If your power factor, suppose your power factor is 70%, you are only using 70 amps. And what happened to the rest of the 30 amps? Almost lost, is sitting there to magnetizing your system. So think of it from an Excel energy point of view. Here they are creating, giving you a wire and a transformer and a relay and all this stuff to give you 100 amp. And you, because of your bad power factor in your building, you decided to take that 100 amp and only use 70 of it. So they're giving you 100 amp, meaning their transmission line, distribution, transformers, everything have to be sized for 100 amp, but you're only using 70 amps out of that. And 30 amps are lost in your building because of magnetism. So who cares? Excel will care now, and you will care too if it's inside your building too. Your power factor could be different from one point to another point, meaning you're just putting a lot of cover that's not used. So how do you correct this phenomena? How do you take 100 amp from Excel and use 100 amp? And oh, by the way, you're only paying for 70 amps when you use the 70 amps. So Excel is pissed off at you because they're giving you 100 amp. You're only using and paying 70 amps out of it. So what do? And why are you using 70 amps? Because your power factor in your building is bad. Why is your power factor in your building is bad? Because you have a lot of motors that have XLs in them that's screwing up the phase shift between the voltage and the current. See where everything is tied together to the XL? No. So how are you going to solve the problem, make the Excel energy happy? You add a capacitor correction. So what do you do when you add a capacitor, guys? When you add a capacitor, you basically raise your power factor. So Excel is giving you 100 amp and you're using 100 amp because there's no losses in your system. So how do you correct the power factor from 70 amp, 70% into 100%? You add bunch of capacitors, XLs, bank of capacitor right at the surface. You add them. By adding them, you shift, we're going to talk about this one in the power factor. You shift the power factor up. Now you are paying for 100 amp and getting 100 amp, and everybody's happy. Can you guys see the big picture? What I wanted from the whole chapter is not to study the phenomena of magnetism. You studied it with Gary. The idea is to get you down to the root of the XL. Why is the XL is a big deal? Can I get rid of it? My question, always when I teach this one, Chris, they asked me, the students will ask, Chad, can I get rid of the XL? Absolutely. Get rid of all your motors and transformers and generators. Then you can get rid of the XL. Can I? No, of course not. If I need an air handling unit induction motor, I can't get rid of my induction motor. Are you kidding me? That's my air handling unit. I have to have a heat in my building. I have to have exhaust the heat in my building. So getting rid of the XL, Chad, is not an option. Getting rid of the XL is not an option. So this is a necessary evil that I have to have. So what do I need to get rid of the necessary evil? Then this to get rid of, not get rid of it, neutralize it. I use the word neutralize it. You're really not getting rid of it. You are neutralizing it by minimizing its effect. So the XL, you neutralize it by minimizing its effect by adding what? Capacitors. That's the whole power factor correction concept. Any question, guys, about the XLXC? XLXC in the power industry?
Is there a reason they don't use inductive heating in residences since they don't penalize you for power factor and residentially?
I think it's efficiency probably. It doesn't cost. I think that's the only thing I probably can think of. Compared here in Minnesota, gas is cheaper. Yeah, residential they don't. Yeah, we don't have a whole lot of. How many motors do we have in residential? And how big are your motors too? It's not just how many. How big are they? You're having a 3 horsepower motors. These are peanuts compared to a 50 horsepower motor, 100 horsepower motor, 300 horsepower motors that you have in a lot of equipments. So, any question, guys, about the XLXC? XLXC? That's really my intention of the whole chapter here. Single phase current calculation, determine volt amps. Now when you get, this is where I want to do some calculation later on, guys, with you, is from now on, moving forward, Phil, you wouldn't talk to Chad about KWs when we talk about equipment. We always talk volt amp. Don't talk KWs. KW is meaningless unless you give me the power factor. So from now on, you're going to be talking about volt amps. So for example, if I have a motor that's running at 15 amps, the 115 horsepower motor and rated for 16 amps, then this motor is consuming out of the system this amount of volt amps. What's the power factor of this motor? I have no idea. What's the power factor of this motor? Can I calculate the power factor if you're giving the amps and the voltage? Can you calculate the power factor? Just the amps and the voltage. Can I calculate the power factor? No. So the power factor phenomena, and that's, we'll talk again with the correction, but let me just jump in here quick. See why mine. Okay, so it's working here. So you're going to have a big phenomenon, guys, called the power, which is called the apparent power. My apparent power always equals the current multiplied by the voltage. This is the single most important. Okay, this is the single most important thing, is the power, apparent power equal the current times the voltage. So, and when you guys start sizing for me, when you size the circuit, so Rob, you came up with a 20 amp circuit for all your receptacles. Based on what? KW or volt amp? Volt amps. We size transformers based on volt amps. We size conduits and wires and circuit breakers based on the volt amp phenomena, not the KW. So, and later on we're going to hear Chad talking about the true power, the one that we consume, the true power. This will equal this I times your V times your power factor. Times your power factor. So suppose that this quantity was 100. Suppose that this quantity was 100, and then you multiply it, suppose, with a 0.7 because your power factor is screwed up. So you take the 100, multiply it by 0.7. What do you get? 70 watt. 70 watt. This is volt amp. Take this, Rob, my friend. Excel Energy is sizing their transmission line to give you 100 volt amp, and you single-handedly, because your building is screwed up with a power factor of 70, you're only consuming 70 watt out of it. And what happened to the other 30 watt? Losses. And what happened to that big conductor coming to your building? Size for 100 watt is sitting there. It's not utilizing it. So that's a big deal. That's a big deal, guys. And I promise we will do voltage drop calculation. A lot of voltage drop calculation. This is just a quick introduction to the impedance. True power. Here's that true power that we just talked about, the watt, guys. Direct current power factor is 100%. We're going to talk about this one. Okay. Faster than the computer. Okay. This is, we just talked about lead and lag. Lead and lag. Lagging power factor. The current is lagging. The voltage is lagging the current. Or the current is lagging the voltage. Voltage wave before current. So here's your lead power factor. Voltage leads the current, meaning the current lags the voltage. The current lags the voltage in an inductive reactance. This is where you want to be. Can you guys see that? Inductance, the current is lagging the voltage. If you put a capacitor, the opposite is true. Now the current is leading the voltage. Current compared to the voltage is constant. The current can lag the voltage, start after, or lead the voltage. Any question, guys, about the XL, XC? Who cares about lead or lag? You need, ultimately, Phil, my friend, if I can have 100% power factor, that's my goal. You can't get 100% power factor. So what do you shoot for? 90 to 96%. Who cares? These, unless you're electrical utilities, I've never seen a low voltage place where you introduce a reactor. Reactors in your building, inductive reactance like in this building, unless you're medium voltage. So most of the time, you're going to be in this situation. You add a couple of capacitors to correct the power factor. What does correct the power factor means, guys? I have my voltage. Suppose my voltage is right here. Look at my voltage from left to right. My voltage started before my current. So my current is my current. My current is lagging. When you add capacitors, look what happens. You keep adding capacitor. You're basically synchronizing the voltage and the current until they start and stop at the same time. Does that make sense? Now, if you keep adding more, what happens if you keep adding more? You're getting into the leading power factor. And we talked about the problem with leading power factor. Here's 100% power factor. That's 100%. If you add more capacitors to 100%, you're going this way. If you add less capacitors, you're going the other way. So ultimately, you want to be hovering around 90 to 96. Ideally, 100 is perfect, but you can't get 100. Can you guys see these signals, what I'm talking about? In sync power factors. That's really my intention of this chapter, is to get you into the XL and XC, because when we start asking you, Nick, my friend, to go size a capacitor bank to add to this building and find the XL, you understand what an XL is. Any question, guys? Any comments about this? Leading power factor. This is one of the most important things. Leading power factor, lagging. If I ask you any building, Chris, my friend, you walk into any building, and if they ask you, is it leading or lagging? 99.9% the building is what? Lagging. How much lagging though? Is it lagging by 95% power factor? Or is it lagging by 90% power factor, which is up to this point 90%, 95, good, we're good? Or is it lagging by 85%, which is not that good, or 60%, which is miserable?
If you had 105% power factor through an excessive capacitance, would you have to add inductance to the circuit?
In a low voltage system, 600 or less, that's the least. That will be my last option. my best option, my first option, if you're medium voltage, yes. If you're doing transmission distribution, medium voltage, yes. In low voltage 600 or less, my first option would be to reduce the amount of capacitance that I have. Because capacitance, guys, in a building like Dunwoody, it mostly created by us. We create capacitors. We buy a bank of capacitors and we hook it up to the system. You're going to see we're going to be doing that. We size the capacitor. So now instead of that big bank, I go unhook that bank, throw it out, and put a different bank. That will be my first option. Not adding in inductive reactance. Yeah. In the low voltage. If you have high voltage, that's a different story. Unity power factor, as I said, when they're both in sync. Look how beautiful things. Isn't that beautiful when everything works as is? What this means, Phil, my friend, means that 100 amp that you got from Excel, that 100 amp, you're paying for 100 amp. It sticks. You're not paying for anything because it's not staying. But the 100 amp that you got from Excel, you're paying for 100 amp and you're consuming 100 amp. Does that make sense? That's what in sync or unity power factor. Look how they start at the same time, cross the zero at the same time, peak, lower peak, and upper peak at the same time, and go back to the zero at the same time. They don't have to be the same. Look at the value. The voltage could be 480 and the current is 5 amps. The voltage, the value could be different, but they are kind of syncing together. They go up together and down together and at different values. Any question, guys, about sync? Your goal when we add a capacitor, that's exactly what we're doing. We're shifting. We don't shift the voltage. The only one who can shift the voltage, guess what? Excel. We shift the current. We have control over the current. The voltage stays here, and by adding capacitor, guess what we're doing? We're telling the current go back until they're in sync, 100%. Done. If you continue going this way, what happened? Leading power factor. What's wrong with the leading power factor? Very bad news. High voltage, equipment will burn. You have a high voltage and your equipment will burn. Does that make sense? So leading power factor is a bad idea. So what happened if I continue moving that red line to the other side? Leading power factor. What does leading power factor means? You plug in, assuming to get 120, you got 150. Who cares? Some equipment will burn. It's as bad as you plug in here, expecting to get 120, and you get 80 volt because of low voltage. Any question, guys, about this? That's what I want to drive through instead of talking about the phenomena and formulas, true power and active power, and let me see if we have and power factor. This is one of the most important formulas, guys, that you can have, which we will study, I promise you, when we do voltage drop calculation. I'll write them down. Example power factor. I'm moving faster than my computer can handle. Okay, so look at this. This is really nice example, guys, about the power factor. I have the ballast input is 90 volt amp. I have 2 lamps in there. That probably just that might be a similar one on your test, guys. So I have a volt amp given on the ballast as 90 amps and two lamps 80 watt each. And they asked me about the power factor. Piece of cake, right? If you know the volt amp and the watt to find the power factor, what would you do? You would take the watts and you divide it by the volt amps. Here's my watts divided by the volt amps. My power factor is 0.88. Is this good, bad, or ugly? It's good. Closer to the 90 is good. Any question, guys, about this? How to find the power factor? How to find the power factor?
Do they attempt to make a correction within the device itself?
Yeah, yes. Some equipment, they have capacitor right at the equipment themselves to correct it.
For the purpose of correction.
Yes, absolutely. Absolutely. Motors, actually, later on when we talk about correction, I'll show you how certain motors you add when you design it. You add the capacitor right with it. So I want to. Here's my apparent power, guys. We'll talk about this one. This is my volt times my amp. Here's my true power equal my volt times my amps. Up to this point, it's still the same. Multiplied by this percentage that's called power factor. How efficient my system is. If you flip this, if you flip it, it becomes power factor equal what? Flip that one. True power over apparent power. This is one of the most important formulas that you're going to have. True power over apparent power. True power over apparent power. Take this example with the green. Suppose my voltage, let's make it simple. My voltage was 240. Suppose my current was 10 to make the calculation. So that will give me 2400, right? 2400 volt amp. 2400 volt amp. Make sense? 2400 volt amp. So suppose my power factor was given. So here's my 2400 volt amp. Multiply this by, suppose my power factor was 90 as it should, 0.9. What would that give me? 2400 times 0.9? 3160. 2160 watt. So out of the 2400 that Excel make available for me, I'm only utilizing, that's what it means. I'm only utilizing 2160 out of the 2400. And that's okay. 90% is okay. My potential use, look at what my potential use, I can go up to 2400 watt by correcting the power factor. My potential use. But I can go as low as utilizing only 2160 out of my 2400 allowance, and I'm okay with that. 90%. Any question, guys, about the power factor? This is really the most important part of the whole presentation here. I'm almost done with this one, guys. Let me just see if we have cost of true power. Cost of true power. Let's take an example of, okay. I want to remind you guys, you only pay for the true power. You don't pay for the apparent power. You only pay for the true power. So for example, if I ask you 100 volt amp, how much do you pay for 100 volt amp? You say, Chad, give me the power factor. That's just the potential use. I need the power factor. If I told you the power factor is 70%, great, now 70 watts. 70 watts, you're going to ask me, how much are we paying per kilowatt? We're paying 7 cents per kilowatt. So you're going to take the 7 cents per kilowatt, multiply it by 70 watt, divided by 1,000 because it's kilowatt. And how many hours you're going to run that baby? 10 hours. Multiply by 10 hours. How many days? 3 days. A year we're going to run it. Or 3 days a week. Or you multiply by the days, and that will give you how many dollars this piece of equipment will consume if you run it at this value, at this power factor. Okay, here's the 24. You need the true power every time you consume it. And I have a couple of examples I'm going to go over, guys, for you. Kilowatt hours and how to calculate the kilowatt hours. The cost. Very simple. If you guys look at this, I have 120 volt multiplied by the amps, and the power factor here is assumed 100%. This is the power factor here is assumed 100%. Otherwise, we can't do that. The power factor is assumed 100%. So here's my watts. The power factor is 100%. Multiply how many hours I want to run this piece of equipment, right? Multiply it by how many days? Divide it by 1,000. Why did I divide by 1,000? Because we pay per kilowatt hour. Paying per watt, guys, is smaller amount. You know, so they do it per every 1 kilowatt will charge you 7 cents. Okay, so divide by 1,000, and then here's what your kilowatt hour that you consume. What's the price that we're paying for? 9 cents. and that's how much it's going to cost you to run this piece of equipment for this amount of time. Any question, guys, about finding the price of? Now, this is simple way. Did you guys go on a tour with Jeff Keldrick, and when he shows you how we pay at Dunwoody? There's demand, and there's demand dues, and there's fees, and it's more complicated than this. They divide, sometimes if you consume certain amount of power at certain amount of time, they charge you this amount. If you, within this amount of time, they charge you a lower amount. So it's more complicated for a commercial than this. It goes by demand too, which is not really hard. I can tell you, 24 hours, the demand on 24 hours is 0.09. If another 4 hours, the demand is 0.2, basically 20 cents, right? Because it's high, peak. And then you do the calculation the same way. Any question, guys, about calculating the cost of power? Always watts, always kilowatts, not even watts. And then you multiply it by the cents, how many cents per kilowatt you do, and how many hours, and then how many days, if any, to find it. Okay. So power factor, when we size electrical discharge luminaires, when we size, guys, volt amp, you always have to size, when you size later on, when we do the power factor correction, I want to remind you from right now, when you guys move, especially when we go to commercial, when we size the conductor, when we size the circuit, everything is sized based on volt amps. If you don't have the volt amps, you need to go find the volt amps. So, for example, I have a load. Look at my load is 7 kilowatt, and with a power factor 85. I need to find the actual load so I can size my conductors. They're giving me the load in kilowatt. Are you kidding me? That's language I don't understand. I need to convert it into a lingo that I can use to size. So you take the 7.2, divide it as they did here by 0.85 power factor. Now you got 8471. This is what you size your transformer based on, your feeders, your branch circuits, your overcome protection device, and everything else. Any questions about this? Any question? Here's my question for you. I have a light like this. Look at the light above your head later on in a commercial building. I'm going to say, if you look at the watts usage of this light, it's using 90, let's just say it's using 88 watt. And I want you to size how many of these lights you can put in a circuit. Can I use the watts? You're going to ask me, Chad, what's the power factor for that baby? I want to tell you the power factor is 90. Now you take the 88 watts for that baby, divide it by 90. You find the volt amp, and then you start adding them on the circuit. We do not size. I can't drive this important. I want you guys to get this message. We size things based on the volt amp, not the watts. So later on, when you guys in the field, you find, especially lights, you find the watts for the light, you're going to have a power factor with it. If you don't have a power factor, it's a good assumption to assume the power factor is going to be kept 0.9.
Is it typically on the label?
It should be. Or if they don't give you the power factor, they give you the amp and the voltage. So you can figure out the amp. So if this is 1 amp and the voltage is 120, piece of cake. It's 120 volt amp. Yep. Effective power factor and sizing transformers. So this is really just to drive the idea that you have to size your transformer based on the power factor, So as I said, now if you look, do I need a transformer 72 kilowatt? If you say kilowatt transformer, everybody knows that you've never been in the electrical industry. I know that my volt amp is 8.75, then my transformer have to be the next standard, which is 10K. So a lot of these guys are calculation that we will be doing that you have to take into consideration the power factor.
Why would an incandescent light have a power factor of 85%?
Did they say incandescent power factor?
go back one step.
Fluorescent, non-continuous lumineers, incandescent power factors.
Static.
Oh, I'm sorry. Okay, how many 20 amp 120 watts are required for 48 100 incandescent? Okay, now they're giving it to you 100% because they have a power factor of 85%. Non-continuous load, they have a power factor. No, this should be fluorescent. I'm not aware of any incandescent lamps that has a power factor of that. So if you want to find it, we will do this calculation, guys. I promise you we'll do a few of these calculations. But first of all, you need to find how many luminaires. You have the 20 amps because non-continuous. Multiplied by 120, give you 2400. Divided by 150 watts, they'll give you 16 luminaires per second. They're not actually using a power factor here. Oh, they're using it here. With a power factor considered, it should be a different story. Now, this is the right calculation because you take 120 amp times 120, right? Give you 2400. That's the capacity of this circuit. Divided by 150 watt, which is volt-amp, because an incandescent lamp is the same thing. What? Give you 16 luminaires per watt. Had this lamp been a fluorescent lamp, that's what they said. Had this lamp been a fluorescent lamp, then you have a power factor of 0.8. So then you divide the watt by the power factor, you get you this. Then you do the whole calculation. You end up with 13 luminaires per fixture versus 16 luminaires per fixture. Would that affect the way you size things? Absolutely. Absolutely. So I can't drive enough, guys. When we size branch circuits, service, everything is based on the volt-amp, based on the volt-amp. Efficiency. The only place that we use, okay, induction. There you go. Power input, power output. I'm going to do a couple of calculations. I'm just going to introduce a concept here. I'll do a couple of calculations about efficiency. Efficiency is one of the only places, guys, where we use watts because that's what we're going to be consuming. So efficiency, you have the power in through the equipment, the power out. Do you expect if you put 100 watt in, you're going to get 100 watt out? That's not a realistic expectation. So when you put some power into an equipment, expecting to get the same amount of power, guys, is the same amount of power is not right because there's losses. So I'll do a couple of calculations. The only thing I want you to get, so there's the efficiency factor. For example, if you have 100 watts here and the efficiency factor is 90, you're going to get 90 watts here out. What happened to the other 10? They got consumed, digested, thrown, wasted in this piece of equipment. We'll do a few calculations, I promise, on the watts and the calculation and so forth. So don't sweat it too hard. Okay. And power in over power out. Okay, I'm going to stop right here. I will do a couple of calculations, guys. In a few here. Any question, guys? Anybody has any question? This is all right.